March 12, 1938, Bridgeport, Connecticut. The factory inspection report from visiting German manufacturing consultants would never fully capture what they witnessed that spring afternoon. American engineers assembling vertical milling machines using casting thicknesses and component masses that defied everything European efficiency engineering said was economically rational. Through the oil-scented air of the East Main Street production floor, massive iron castings moved through assembly stations with deliberation that seemed wasteful to European observers. No lightweight magnesium alloys, no pressed steel shortcuts, no cost-saving design compromises. Components so thick and heavy that German engineers calculated 40% material excess compared to their own precision mills producing identical work. In European machine shops, modern manufacturers had spent the 1930s pursuing weight reduction and material efficiency. Advanced metallurgy allowed thinner castings that maintained rigidity through scientific geometry rather than brute mass. Sophisticated stress calculations meant components could be engineered to exact requirements without safety margins that European efficiency experts considered primitive waste. The Americans were operating with a manufacturing philosophy the Germans found economically irrational. Cast iron bases weighing 800 pounds more than necessary, spindle housings machined from solid steel blocks rather than fabricated assemblies bearing systems overbuilt by factors that seemed to violate basic engineering economics. 5,000 miles from European efficiency standards, the most significant durability revolution in manufacturing history was taking shape. Not in advanced materials or sophisticated calculations, but in massive oversizing that eliminated failure modes entirely. Russell Fenton stepped through the brass doors of Bridgeport Machines Incorporated on a cold January morning in 1937, carrying mechanical engineering credentials from MIT and design philosophies shaped by Depression-era caution. The company had been manufacturing milling machines since 1938. But the economic collapse had forced a fundamental rethinking of their design approach. Traditional pre-Depression manufacturing had emphasized initial cost reduction and competitive pricing. Mills were designed to minimum specifications that satisfied immediate performance requirements while keeping purchase prices accessible to cost-conscious shops. The philosophy had seemed sound until the economic catastrophe revealed its fatal flaw. Shops that had purchased bargain-priced machines in 1928 found themselves unable to afford replacements when those machines wore out 5 years later. Fenton's assignment was deceptively simple. Design a vertical milling machine that would never need replacing. The economics were counterintuitive. A mill priced 20% higher but lasting 40 years would cost to shops far less than a cheaper machine requiring replacement every decade, but achieving 40-year lifespan required abandoning every cost-saving principle that had dominated pre-Depression design. The solution emerged from systematic analysis of failure modes in existing mills. Fenton spent weeks examining worn-out machines from shops throughout New England, documenting every fracture, every worn bearing surface, every misaligned component. The pattern was undeniable. Machines failed, not because of catastrophic breakage, but through gradual dimensional changes as castings flexed under cutting loads, bearings wore from inadequate mass to absorb vibration, and components shifted as lightweight assemblies loosened over years of operation. The design principles Fenton developed for Bridgeport's 1938 series violated every efficiency standard that dominated contemporary engineering education. While European manufacturers calculated exact stress requirements and designed components to meet those specifications with minimal material waste, Fenton's approach seemed to abandon calculation entirely in favor of brute oversizing. The base casting provided the clearest example of his radical philosophy. European mills of comparable capacity utilized bases weighing 1,200 to 1,500 pounds. Carefully shaped with ribbing patterns that provided maximum rigidity per pound of iron. Scientific stress analysis allowed engineers to place material exactly where loads required support while minimizing excess mass. Fenton's design specified a base casting weighing 2,300 pounds, nearly double the European standard for identical working capacity. The thickness was extraordinary. 4 inches of solid cast iron, where European designs used 2.5 inches with reinforcing ribs. The additional mass served no immediate structural purpose that contemporary engineering could justify. Marcus Whitfield, chief engineer at Cincinnati Milling Machine Company, examined Bridgeport's prototype design drawings during a March 1938 industry conference with barely concealed skepticism. The specifications seemed to ignore everything modern engineering had learned about efficient structural design. Whitfield's own mills achieved identical cutting capacity with bases weighing 1,600 pounds through careful stress analysis and optimized geometry. The spindle housing illustrated Fenton's departure from conventional practice even more dramatically. Standard industry design utilized fabricated steel assemblies, multiple components welded or bolted together to create the housing that supported the cutting spindle and its bearings. The approach allowed manufacturers to use appropriately sized materials for each section, minimizing cost and weight. Bridgeport's specification called for the spindle housing to be machined from a single forged steel billet weighing 480 pounds before machining. The final component retained 320 pounds after removing material to create bearing bores and mounting surfaces. Contemporary designs achieved equivalent functionality with fabricated assemblies weighing 160 pounds. Industry publications questioned whether Bridgeport understood basic engineering economics. The American machinist ran calculations demonstrating that the material costs alone for Fenton's overbuilt design exceeded the total manufacturing cost of comparable European mills. Engineering magazine published editorials suggesting that Depression-era desperation had driven American manufacturers to abandon rational design principles. The bearing systems represented perhaps the most extreme example of Fenton's oversizing philosophy. European mills used precision-tapered roller bearings, carefully sized to support calculated spindle loads with appropriate safety factors. The bearings were engineering marvels, capable of supporting tremendous loads while maintaining precise spindle positioning through sophisticated geometry. Fenton specified bearing assemblies 3 times larger than load calculations indicated necessary. The massive bearings could support cutting forces far exceeding anything the mill's motor could generate. The excess capacity seemed wasteful until Fenton explained his actual design intent. The bearings weren't sized for maximum cutting loads. They were sized so that normal operating loads represented such a small fraction of bearing capacity that wear would be essentially immeasurable over decades of continuous operation. Production methods at Bridgeport's expanded East Main Street facility during 1938 and 39 reflected the same deliberate excess that characterized Fenton's component designs. While European and most American manufacturers pursued assembly line efficiency, Bridgeport's approach seemed to deliberately reject productivity in favor of precision that contemporary standards considered unnecessary. Each mill required 140 hours of assembly time, nearly 4 weeks of careful fitting, alignment, and testing before the machine could be approved for shipment. Industry averages for comparable mills ranged from 40 to 60 hours using modern assembly techniques and interchangeable components. Bridgeport's process consumed more than double the labor hours competitors required. The spindle assembly procedure illustrated the meticulous approach that made conventional efficiency engineers uncomfortable. European manufacturers had perfected interchangeable spindle assemblies that could be installed in 30 minutes using standardized mounting interfaces and pre-measured bearing preload specifications. The operator simply bolted the completed spindle assembly to the housing and verified runout with a dial indicator. Bridgeport's method required 2 full days. Assembly technicians spent the first day hand-scraping the spindle housing bore, removing microscopic amounts of cast iron to achieve surface contact that exceeded 90% across the entire bearing surface. Modern manufacturing considered such hand-fitting unnecessary. Precision grinding could achieve adequate bearing surfaces in minutes rather than the 8 hours required for hand-scraping. The bearing installation process was equally time-consuming. Rather than using standard preload specifications from bearing manufacturers, Bridgeport technicians individually tested each bearing assembly under simulated cutting loads. They measured heat generation, vibration characteristics, and microscopic deflection under various load conditions, adjusting preload until performance met specifications that exceeded industry standards by substantial margins. James Morrison, production manager at Bridgeport's main competitor Brown & Sharp, visited the East Main Street facility in September 1939 and returned to Providence, shaking his head at what he considered manufacturing inefficiency, bordering on economic irrationality. The time and labor Bridgeport invested in each machine could produce 2.5 mills using modern assembly methods. The alignment verification process consumed another full day of assembly time. After the spindle and all major components were installed, technicians spent hours measuring perpendicularity between the spindle axis and table surface at dozens of positions across the full table travel. Industry standards specified verification at 4 positions. Bridgeport checked 64 positions and adjusted until deviation measured, less than 2/10,000ths of an inch across the entire working envelope. The final testing protocol required running each completed mill for 16 hours under varying loads and speeds while continuously monitoring vibration, temperature, and dimensional accuracy. European manufacturers tested sample machines from each production batch. Bridgeport tested every single unit before it could be approved for shipment. The economic implications seemed devastating. Material costs exceeded competitors by 40%. Labor hours more than doubled industry averages. The resulting purchase price placed Bridgeport mills in the premium category that only the most prosperous shops could afford during the lingering effects of the Depression. Market response to Bridgeport's 1938 series initially seemed to confirm industry skepticism about Fenton's overbuilt design philosophy. During the economically uncertain months following the mill's introduction in late 1938, orders trickled in at rates that threatened the company's financial survival. Shop owners struggling with Depression-era budgets could not justify the premium pricing that Bridgeport's massive construction required. Thomas Harrigan, owner of Harrigan Machine Works in Worcester, Massachusetts, represented the typical customer reaction when Bridgeport's sales representative demonstrated the new mill in February 1939. The machine's capabilities were impressive. Rigidity that allowed heavy cuts without chatter, spindle precision that held tolerances through extended operations, build quality that seemed indestructible. But the purchase price exceeded comparable machines by nearly 30%. Harrigan's shop operated 3 European-built vertical mills purchased in the late 1920s. They performed adequately for the automotive component work that sustained his business through the Depression. Spending premium prices for marginally better performance made no economic sense when every dollar counted toward survival. He ordered a less expensive Cincinnati machine instead. The transformation in market perception began not through marketing or demonstration, but through something Bridgeport's engineers had never anticipated. Machines that had entered service in late 1938 and early 1939 simply refused to wear out. By 1942, shops that had purchased the first Bridgeport mills were reporting dimensional accuracy that remained within original specifications despite 3 years of continuous heavy use. Marcus Chen operated a small job shop in Hartford producing precision components for the expanding defense industry. His Bridgeport mill, serial number 147, had run 2 shifts daily since March 1939. Producing thousands of components under cutting conditions that would have worn out conventional machines. Yet when Chen checked spindle runout in December 1942, the measurement showed 1/10,000th of an inch, identical to the acceptance test measurements from 3 years earlier. The phenomenon was being reported across New England as the first generation of Bridgeport's overbuilt mills accumulated operating hours that should have degraded their precision. Traditional mills showed measurable accuracy degradation after 12 to 18 months of hard use. Spindle bearings developed play, base castings showed detectable flexure, alignment specifications drifted beyond original tolerances, normal wear that required periodic rebuilding or eventual replacement. Bridgeport's massive construction was revealing an unexpected property, components so oversized that normal operating loads represented such a small fraction of their capacity that measurable wear essentially did not occur. The 4-inch thick base casting flexed less under maximum cutting loads than conventional castings flexed under moderate loads. The enormous spindle bearings were operating at loads so far below their rated capacity that projected service life calculations suggested they might last decades rather than years. Word spread through manufacturing networks with the credibility that only actual shop floor experience could provide. These machines were not wearing out. World War II production demands provided the ultimate test of Fenton's oversized design philosophy. As defense contracts flooded American machine shops beginning in 1941, Mills that had entered service in 1938 and 39 faced operating conditions their designers could never have anticipated. 3-shift operations, inexperienced operators, maximum material removal rates, minimal maintenance attention as skilled machinists moved to more critical work. Traditional mills collapsed under the relentless demands of wartime production. Shops throughout the industrial Northeast reported catastrophic failures of machines that had performed adequately under peacetime conditions. Base castings fractured from thermal stress as machines ran continuously without cooling periods. Spindle bearings failed after months of maximum load operation. Alignment specifications drifted as lightweight components flexed under the sustained heavy cutting that defense work required. The Pratt & Whitney plant in Hartford operated 47 milling machines by December 1941, when Pearl Harbor transformed their aircraft engine component production from commercial work to maximum military priority. 23 of those machines were conventional pre-war designs from various manufacturers. 14 were Bridgeport, 1938 series mills that had entered service between 1939 and 41. Production manager Robert Lansing kept detailed maintenance records that would later reveal the dramatic performance difference between conventional and overbuilt designs. By June 1943, 18 months into maximum production demands, 17 of the 23 conventional mills had suffered major failures requiring extensive rebuilding or complete replacement. Cracked base castings, worn spindle bearings, misaligned components that could no longer hold tolerances. All 14 Bridgeport mills continued operating within original specifications. The massive castings that had seemed economically wasteful in 1938 were absorbing wartime abuse that destroyed conventionally designed machines. The enormous spindle bearings showed no measurable wear despite operating continuously under loads that exceeded peacetime levels. The hand-scraped bearing surfaces maintained their precision despite thermal cycling that would have degraded normal machine surfaces. By late 1944, shops that had dismissed Bridgeport's premium pricing were desperately seeking the overbuilt mills that could survive wartime conditions. Production delays from machine failures were costing defense contractors far more than the initial price premium would have represented. A conventional mill costing 30% less than a Bridgeport, but requiring replacement or major rebuilding after 2 years of wartime service, was enormously more expensive than the overbuilt design that simply continued running. Thomas Harrigan, who had rejected Bridgeport's sales pitch in 1939, watched his 3 European mills fail one after another during 1942 and 43. The Cincinnati machine he had purchased instead of the Bridgeport required spindle replacement in early 1943. By March 1944, he was operating 2 Bridgeport mills purchased at wartime premium prices and a single rebuilt European machine that could no longer hold close tolerances. His only regret was not buying Bridgeport in the first place. The post-war decades revealed the full extent of Fenton's engineering achievement as Bridgeport mills from the 1938 series continued operating long after every conventional machine from that era had been scrapped or rebuilt beyond recognition. By the 1960s, shops throughout America were running 25-year-old Bridgeport mills that maintained accuracy specifications. Contemporary machines struggled to match. Harold Peterson purchased Precision Components Incorporated, a small Minneapolis job shop, in 1963. The facility came with 8 milling machines, including 2 Bridgeport 1938 series mills, serial numbers 321 and 489. Both machines had been in continuous operation since their original installation in 1939, accumulating over 50,000 operating hours each. Peterson's background in modern manufacturing made him skeptical of the ancient Bridgeports. 25 years of operation should have degraded them into scrap metal suitable only for recycling. Yet dimensional checks revealed the machines still held tolerances within 0.2 of an inch across their full working envelope. The spindle bearings showed no measurable play. The massive base castings remained perfectly rigid under maximum cutting loads. The comparison with contemporary machines proved startling. Peterson operated 3 Cincinnati mills purchased in the late 1950s that already showed accuracy degradation requiring periodic adjustment and compensation. The lightweight castings had developed detectable flexure under heavy cuts. The spindle bearings required replacement after 4 years of operation, yet the Bridgeports from 1939 simply continued functioning as though age had no meaning. Throughout the 1970s and 80s, as manufacturing technology advanced through numerical control and eventually computer numerical control systems, the old Bridgeport manual mills refused to become obsolete. Shops discovered that for certain applications, the massive rigidity and mechanical simplicity of the 1938 design outperformed modern CNC machines costing 10 times as much. James Chen, son of Marcus Chen, who had purchased serial number 147 in 1939, inherited his father's Hartford shop in 1982. The original Bridgeport mill still occupied its position on the shop floor, now 43 years old, but continuing to produce precision components with reliability that Chen's newer CNC equipment could not match. The electronic controls on his modern mills required constant attention and periodic, expensive replacement. The Bridgeport required occasional oil changes and nothing more. By 1990, Bridgeport mills from the 1938 series were achieving legendary status among machinists who understood what continuous 50-year operation meant. These were not museum pieces carefully preserved under ideal conditions. They were working machines that had run 2 or 3 shifts daily for half a century, accumulating operating hours that should have destroyed them multiple times over. Yet they continued functioning with accuracy and reliability that seemed to mock the planned obsolescence characterizing modern manufacturing equipment. The 21st century has revealed the ultimate vindication of Fenton's oversized design philosophy as Bridgeport mills from 1938 continue operating in shops throughout America now over 80 years after their manufacture. These machines have outlived not just their original operators, but entire generations of replacement technologies that were supposed to render them obsolete. Modern CNC mills typically achieve 10 to 15 years of service life before electronic failures, worn ball screws, or structural fatigue require replacement. The lightweight castings and high-speed components that enable CNC capabilities also ensure relatively short service lives. Controllers become obsolete as software advances. Precision components wear as they operate at speeds the 1930s engineers never imagined. Peterson Manufacturing in Minneapolis still operates serial numbers 321 and 489, now over 80 years old. The machines have been rebuilt exactly once in 1996, a process that involved replacing worn way surfaces and overhauling the spindle bearings. The original 4-inch thick base castings remain perfectly rigid. The massive spindle housings show no structural degradation. The hand-scraped bearing surfaces, reground during the 1996 rebuild, should be good for another 40 years. The economic comparison has become almost absurd. A modern CNC vertical machining center costs $80,000 to $120,000 and requires replacement every 12 to 15 years. Over an 80-year period, a shop would purchase 5 or 6 machines, spending $450,000 to $700,000. Serial number 321 cost $850 in 1939, equivalent to perhaps $18,000 in current currency. Add one major rebuild in 1996 for $12,000. A total of 80 years cost $30,000. The engineering lesson has profound implications for modern manufacturing equipment design. Fenton's approach of massive oversizing to eliminate failure modes entirely created machines that operate so far below their structural limits that normal wear essentially does not occur. Contemporary designs optimize for minimum material use and maximum performance, creating machines that operate near their limits and inevitably wear out. Small shops throughout America still rely on these iron survivors from the 1930s. The machines represent more than nostalgia or preservation of history. They are economically rational choices that outperform modern equipment for many applications. The massive rigidity prevents chatter during heavy cuts. The mechanical simplicity means repairs require basic tools rather than expensive electronic diagnostics. The proven durability eliminates the uncertainty of equipment replacement planning. Russell Fenton died in 1979, but his engineering philosophy lives on in thousands of machines still running in shops from Boston to Los Angeles. The mills that Depression-era engineers laughed at for their wasteful excess have outlived every critic, every competing design, and entire technology generations that were supposed to make them obsolete. Simple engineering, massive cast iron, and precision craftsmanship created machines that will likely still be producing accurate parts when current CNC technology has been forgotten.